All right, hello Precalc 12. So I am going to skip the last part of the rational functions unit. I think it's not. Miss Power had mentioned that she might be doing that, and I think that that's not a bad idea. So I'm also going to follow suit, and I'm going to get into sequences and series. And I think that should be reasonable, and you have the stuff that you will probably need going forward for rational functions. So sequences and series, they're kind of funny because you don't use them a whole lot in first semester calculus, but they're really important for understanding integration. When you set up integration the first time, you kind of do things that you use Riemann sums, and Riemann sums are basically all just summations. So it's this idea of sequences and series. Now, specifically, we're going to pay attention to something known as an arithmetic sequence of series and a geometric sequence in series. So the two different types, arithmetic and geometric. And sequences and series, we'll talk a little bit about what the difference is between those and what it means. But for the time being, we're just going to jump right into this idea of arithmetic sequences and series. Problem is, it's from the grade 11 textbook, so we'll try to find a way to work with that. So 1, 2, 3, here we go. So a sequence, and I know you can read, but I'm going to read it anyway. Sequence is an ordered list of objects. The individual objects are referred to as elements or terms. These terms follow a pattern or rule in order to determine the next term in the sequence. You've probably bumped into a whole lot of these that were just games somewhere along the way. So it's basically just an ordered list of objects that follow some sort of pattern or rule. Anyway, that's all the sequence is. And so we can refer to a specific term within a sequence by using a subscript method. So you've probably done something like a subscript method. If you've taken any physics, you definitely used it before. Chemistry uses some subscript methods too. They've shown up for us, I think, as well a little bit. But basically the idea is you are going to write things down just using a labeling method. So if you write t with a little 1 down below in the subscript position, so usually exponents are written in what are called the superscript position. So superscript position, subscript position, and in this case, if it was t1, that means term 1. Sometimes people will start with t0. I generally like to do t1 as the first term, and find with students it seems to go a little bit better. Second term being t2, and then the nth term, which is just some unknown later term, could be referred to as t sub n or tn. All right, now finite sequence is one that has a certain particular number of terms to it. So in the one that I have written up there, I have it written in set notation. Set notation is or set builder's notation. This one just says we have a set, and we have the element 1, and the element 2, and the element 3, and the element 4. That's term 1 is 1, term 2 is 2, term 3 is 3, term 4 is 4. That's a finite sequence. It's done. You can also have infinite sequences. You can tell my curly braces need a little bit of work, but that's all right. I'll pretend you know what I'm talking about when I do these little random squiggles. All right, so for an infinite sequence, it just doesn't have a defined number of terms. So if I had like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it just was allowed to keep going and going, there's no end to that particular sequence. So it would be infinite. This may or may not, probably not, but it may be familiar to you. This one is known as the Fibonacci sequence, and so it goes 0, 1, 1, 2, 3, 5, and then it's asking you what is T12. So without telling you how to do it, if you want a little adventure and you haven't seen it before, pause and see if you can figure out what the next term would be, and then from there figure out the one that would be labeled as T12. So if we call the first one T1, so that'd be T1, T2, T3, T4, T5, T6. Those are the ones that we can see there. If you could get T12, go for it. If you need a little bit of a nudge in order to try to get T12, you might try noticing that the pattern has something to do with addition. If you still need another nudge, then you might want to know that this is a recursive, or it can be written recursively, which means that the future terms are made up with terms that have already happened. So if you put together that adding and the terms that have already happened thing, you might notice that you get something like the following. 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 would be 8. And then 5 plus 8 would be 13. And then 8 plus 13 would be 21. 13 plus 21 would be 34. 34 plus 21 would be 55. And I can't remember which one term 12 is. So you just keep going and make sure you've counted and labeled them until you find out which term you're looking for. So again, that's known as the Fibonacci sequence. That is an infinite sequence, as you can see with the ... that happens afterwards. There's no defined end to it. It would just keep going and going and going. And it can be written, as I said, recursively, where Tn is equal to Tn minus 1 plus Tn minus 2. So basically, whatever term you're looking at is just made up of the last two terms added together. I can write that down just in case you're wondering. We don't do a whole lot of recursion right now, and this is not arithmetic or geometric. It's just for talking about. But if I say Tn is made up of Tn minus 1 plus Tn minus 2, that could be a way to write that recursively. An arithmetic sequence is an ordered list of terms in which the common difference, or the difference between the consecutive terms, is constant. In general, this means that so T of n is equal to T of n minus 1 plus d. So you just basically take the last term that you had, and then you add on d, and d is going to be a common difference. So it's the same thing every time. So if I told you, for instance, that we had T1 is equal to 8, and the common difference is 3, and I asked you, well, what is T2? Well, T2 then would be, according to this, Tn is equal to Tn minus 1 plus d. Well, your common difference is 3. The last one you knew was an 8, so the next one is going to be the 8 plus 3, which is 11. Then we add another 3 on there, which is 14. And we add another 3 on there, which is 17. And we add another 3 on there, which is 20. And we add another 3 on there, which is 23. And you probably get how that's going. So this is known as an arithmetic sequence. So it would be, if we put it in these curly braces, 8, 11, 14, 17, 20, 23, blah, blah, blah. And we could make that go on forever, or we could cap it off somewhere and make it finite too. But for this, it seems like no real reason to cap it off. So we could plus ... And we'll just follow that same pattern forever. Oh dear, big yawn. All right, yeah. I wonder if you're yawning on your side of the camera. I'm sorry if I made that happen on your end. My apologies. So, it says here that Tn is equal to Tn minus 1 plus d. Tn minus 1 is equal to Tn minus 2 plus d, which means that Tn is equal to Tn minus 2 plus 2d. Now, it says, how could we express Tn in terms of T1? Now, I don't know if I didn't do it there. So let's think about that. So if Tn is equal to Tn minus 1 plus d, and Tn minus 1 is equal to Tn n minus 2 plus d. And we want to somehow, well, we're going to put this into this position, which means Tn would be equal to Tn minus 2 plus d. So plus 2d. So it depends on how far back you have to go to get to T1. So if the goal was to write down Tn is equal to T1, then can we do that? Well, the answer is yes. Maybe the n's actually might be throwing you off a little bit. So T2 would be equal to T1 plus d. And T3 would be equal to T2 plus d, which is the same thing as T1 plus d. So it's equal to T1 plus 2d. So T4 would be equal to T3 plus d, which is equal to T2 plus 2d, which is equal to T1 plus 3d. So you might notice a bit of a pattern here. Tn is equal to T1 plus. See if you can figure out what that would be. You're going to get some sort of number of d's in there. So when it was a 2, we have 1d. When it was a 3, we had 2d's. When it was a 4, we had 3d's. So how are those related? Well, 2 and 1, and 3 and 2, and 4 and 3. It appears like it's always one less d than the term number. And in this case, we have term number n. So what's 1 less than n? Well, it's n minus 1. And so we could say that term number n is equal to term 1 plus n minus 1 times d. And so this, which usually I have written in here instead, so I guess I could do it this way. I'll show you math type. I don't know if you've seen this before, but I use an old version. I don't know. I don't want to purchase to get the new one. Let's see. Oh yeah, I want to do t sub. So sub n is equal to t sub 1 plus n minus 1 times d. All right. That formats things pretty nicely, so we'll just do that and put it in here. So there we are. That would be a way to describe Tn in terms of T1, and no other terms needed there. So we could skip right from the first term to some nth term. Now, in context of what we had just been working on, when I had said T6 was 23, for instance, what we just said is that T6 would be equal to T1 plus 5 times d. We know our common difference is a 3, so that means that T6 is equal to 8 plus 5 times 3. 5 times 3 is 15, plus 8 is 23, which is exactly the same thing that we had there. The benefit to that is you never need to know what term 2, 3, 4, or 5 are. It's not that important if the list was like this, where it is only like 6 things long. But if I asked you what T100 was, you would be much happier to use the general term to be able to use T1 and 99 times the common difference. In the example we just had, if I wanted T100, that would be equal to 8 plus 99 times 3. And so 8 plus 99 times 3, so that would be 100 times 3 would be 300, so it's 297, is equal to 305. So that's much shorter than counting up every single one of the 100 terms that are involved there. So kind of nice. All right, so here is a problem that's from the text, actually. It says, determine a particular term. A visual and performing arts group wants to hire a community events leader. The person will be paid $12 for the first hour of work, $19 for 2 hours of work, and $26 for 3 hours of work, and so on. write the general term that you could use to determine the pay for any number of hours worked. What would the person get paid for 6 hours work? Actually, it's kind of a peculiar thing to do, this sort of thing. It's kind of just a linear function, but that's okay. We're going to do it as general term for creating a sequence. So this one is going to be, now it's kind of funny because, yeah, I'm going to just say that T1 is equal to 12. I know that T2 is equal to 19. I know that T3 is equal to 26. So the common difference here is a 7. So I can say 7, 7. I can see it right there. So what I'm going to say is that my Tn is equal to T1 plus n minus 1 times the common difference of 7. So that would be a general term that can be used to determine the pay for any number of hours worked. If I wanted to know specifically for 6, we could say, well, what's T1? Well, I know that's 12 plus 6 minus 1 times 7, which is going to be 5 times 7 is 35, so 47. And that would be what somebody would get paid using this particular setup for 6 hours of work. I'm going to skip that one for now. So this actually no, you know what? It's not a bad one. I'm going to go back to it. So the musk ox and caribou of northern Canada are hoofed mammals that survived the Pleistocene era, which ended 10,000 years ago in 1955. The Banks Island musk ox population was approximately 9,250 animals. Suppose that in subsequent years, the growth of the musk ox population generated by an arithmetic oh, yeah, it is. It reads fine. I just, I thought there should be an is in there, but nope. An arithmetic sequence in which the number of musk ox increased by approximately 1,650 each year. How many years would it take for the musk ox population to reach 100,000? All right, so this is kind of a backwards question. So we know that our Tn that we eventually want to have is, now this might not be true that it is actually, well, it does say reach 100,000. It gets a little bit dicey if it's not exactly 100,000, but we'll be able to fix it by looking at the non-whole number n that we would end up getting. But I'm going to put it in as 100,000 right now. We do know that the common difference is 1650, and right in 1955, which I'm going to call term 1, is in the 1955, there were 9,250 animals. And so it's increasing. So let's go. Tn is equal to T1 plus. Now, this is where it's kind of weird because normally I use n minus 1 here, which is kind of right. But I want to actually know how many common differences, because it would be the number of years past 1955 that I'm interested in. So the number of common differences is going to be, I'm just going to call it n, and each of those common differences is 1650. So if 1 year has passed, then it would be a 1n. 0 years have passed, we're just stuck, and we're in 1955, and it's 9250 in terms of what's going on there. So we would get 100,000 animals. That's our Tn. It's equal to 9250 plus n times 1650. I'm going to have to reach probably for a calculator here. All right, so that is almost 10,000. So it's going to be 90,750, I think, is equal to n times 1650. Oh, how much do I feel like struggling? Those are some relatively large numbers. So it should be okay for the first part. So that's going to be what? 5,000 would be divided by 5 would be 25, and then 5 goes into 90 18 times, so it's 18 25 over 33. I don't think I'm. Is that divided into 3? 9 is 7. Nope. All right, so I'm gonna just chuck her in. First of all, let's see if I did the first part right, because that would be awkward. 33, and then versus 97, 50 divided by 16. Oh, I didn't. What did I do? Obviously, it's in the last part in my reduction there. 5 goes into 90. 18 and then 75. Oh, 15. Oh, stink. I don't know why I put 25. Well, I do because I messed it up, but 18, 15. All right. So that, let's just double check that. 18, 15 divided by 33. Hey, 5. Hey. All right. So at that point, would I have had, oh, it does divide by 3. So I would have had a little more luck there. So it would have been 11 over 6 and then 5. Yeah, it's just not the friendliest thing. I wouldn't have had much luck. All right. So even if I had been able to do math, I probably would have had to reach for something to 11 times 55, 605. I suppose I could just have tried it, but oh well. So 55 years have passed. Long story short, a lot of mumbling. I don't know. This is just use a calculator on this line. You're good to go. 55. I actually have a calculator sitting about 3 inches away from me. Probably could have used that. All right. Jonathan has a part-time job at the local grocery store. He's been asked to create a display cereal boxes. The top 6 rows of his display are shown. They are not shown. The number of boxes in the rows produced in arithmetic sequence. There are 16 boxes in the 3rd row from the bottom, 6 boxes in the 8th row from the bottom. So it's kind of like this, it's a display where the bottom row is the biggest, and then it's like less, and then less, and then less, and less, and then less. And it says how many boxes are in the bottom row, and then determine the general term for the sequence, and what is the number of boxes in his display. So the 3rd row from the bottom, I would call that probably the 4th row. That would be my interpretation. I don't know. 3rd row from the bottom. Bottom row, 2nd from the bottom, 1st from the bottom. Yeah, I guess you don't say 1st from the bottom. We'll call that 3rd row then. So the 1st row, I don't know how many are there. In the 2nd row, I don't know how many are there. 3rd row, I do know how many are there. There are 16. And then in the 8th row, oh gosh, I hope I gave myself enough room. 4, 5, 6, 7, 8. And then in the 8th row, I have 6 boxes. Obviously, this is definitely to scale. So, what do I know? This is a stack that looks something like this. If I were to take T7, which is 6, and I take T3, which is 16, I do know that T7 would be equal to T1 plus 6 times D. And I know that T3 would be equal to T1 plus 2 times D. Because of our general term thing, where we have Tn is equal to t1 plus 1 less than n times d. So in this case, if I'm using 7, then it's 6 common differences, and if I'm using 3, it's 2 common differences. I'm going to use a technique from grade 11, elimination. Think of it as a system of linear equations, actually. And we're going to take this and subtract this. And so I would get that t7 minus t3 is equal to t1 minus t1. Gone. 6d minus 2d is 4d. But I actually know what t7 and I know what t3 are. There's 6 and 16. So I would get something that only has d in it, which is great. So this negative 10 is equal to 4d. It's the 8th row. I don't know why I put 7. It's the 8th row. I was like, oh, that's weird that it doesn't work out to be a whole number of cans. Probably should start that over again, but I'm not going to because I'm running out of time. I have a meeting in 35 minutes. I need to make sure that this gets done. My apologies. I'm sorry. So T8 is equal to, so that means that that is actually a 7 instead of a 6. And the difference will be 5, which will work out nicely. So 7. And then, so when we subtract them, t1 minus t1 is still the same thing. But 7d minus 2d is 5d. And so we will get negative 10 is equal to 5d, or we get a common difference of negative 2. So now this time, when we add on the d, it's a negative 2, which is fine. So how many boxes are in the bottom row? So if I put that negative 2 back up into one of my equations, I'm going to put the t3 is equal to t1 plus 2d. Well, I know my t3, that's 16. My t1 is what I'm looking for. And I know now that my common difference is actually a negative 2. So if I put the negative 2 in there, we get negative 4 plus t1 is equal to 16. Add 4 to both sides and get 20 is equal to t1. So we get a t1 of 20. 20 boxes on the bottom row. So that is A. My general term then is Tn is equal to T1 plus n minus 1 times d, which means that Tn is equal to 20 plus n minus 1 times negative 2 in our case. So we found that the common difference is a negative 2, and we found that the first term was a 20. So now, if I wanted to know what is the number of rows of boxes in the display, now we know that it goes down by 2 every time. And it's an even number of boxes in each one of the rows. So it's going to be like 6, 4, 2. 2 is going to be the last one because 0 isn't really a row in the display. So I could just say, well, I know that there's 6 left at 8, so it's going to go down to 4 at 9 and then go down to 2 at 10. Or I could say, well, since I know it's going to be 2 for my Tn, and I can use this little equation that I came up with, then subtract 20 from both sides, get negative 18 is equal to n minus 1 times negative 2. Divide negative 2 both sides, get 9 is equal to n minus 1. Add 1 to both sides, you get row 10. So again, like we said, row 8 has 6, row 9 would have 4, row 10 would have 2. And so that gives us that row 10 is 2. All right. Gonna do a little intro to series. So this I really like this little story. I don't know how true it is, but and depending on where you read it, it's slightly different in terms of either punishment or challenge or whatever. But Gauss, who is credited with kind of coming up with this on a whim during elementary, the thing that we're going to look at in just a second, or at least a portion of it. Here we go. So he was challenged to find the sum of all numbers between 1 and 100. Teacher had planned it to take a while, but Gauss responded very quickly. So how can you sum 1 to 100 quickly with basically without summing 1 to 100, not all of the individual terms. So this is going to be a really cool, really subtly beautiful solution. So if I take all the numbers and I were to write them in order, and I were to take all the numbers and I were to write them in descending order, it would look kind of like that. If I were to take those two lists and add them, I would notice that it gives me the exact same value every time. How many 101s would I have? Well, I'd have the same number of 101s as the number of digits in, or sorry, not digits, the number of values in my original list. So my original list is from 1 to 100. That's 100 different values. So I have 100 different sums of 101. Great. But that's not the answer, because this is actually two of the lists. I took the same list and put it in and added it, but I don't want two lists. So 2 times the lists, or the answer, I don't know what to call it, 2 times, I'll just say x is equal to this thing, but we actually just want 1x. So in this case, we're going to get that x is equal to, so that's what, 10,000, but another 100 in there, so 10,100 divided by 2, which gives us 50/50. All right, so there it is. That's the sum. So it's 50/50. So if you took 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, and you did it all out by hand, or even if you punched it into a calculator without knowing a quick way to tell your calculator to do it, it would take you a little bit. This method gives us the answer very, very quickly in a very nice, tidy way. So thank you, guys. One of the ways that you can tell a calculator to do something quickly is if sometimes your calculator might allow you to do sigma notation. So sigma notation is this idea that we have a way to represent repeated addition. Now you might say, I know repeated addition, that's just multiplication. Yes, kind of, which is why the common difference is 2 times, or n minus 1 times common difference. So you do get that in there. But if you start offset, so your t1's not 0, then it's not just straight multiplication. And there are other types of sequences and series, which is what we're looking at right now, or we're going to be looking at here, where you might not want to represent, or there's different ways to come up with it, so not just multiplication. So if I wanted to take what we just did, all of the first 100 whole numbers, and I wanted to sum them, if this is my sequence, so this was sequence, is that set, then I could say S100 is the sum of the first 100 terms of the sequence. So this is not term 100, which is just, hey, look at the last one. This is sum of all of them. So it would be the, actually, I think I don't want that label. So it would be S100 is the sum of the 100 terms in this particular sequence. So another way to write that, though, is what I have written right here. This is known as sigma notation. So I think, oops. So there's a little lowercase sigma that looks kind of like that. And this is an uppercase sigma. and that uppercase sigma is kind of equivalent to the letter that we use in English for S, and it goes along with sum as well. So this is a summation, a sigma, starting at an I value of 1, going up to an I value of 100 of Ti. So what sigma notation tells you to do is it tells you to make a new inside for every number that you would go through on the outside. So you start at the bottom number, which is a 1, and then it would say, so write down the inside, and then this notation, sigma notation, means add. So we would take the number that's on the inside, the thing that's on the inside, evaluate it at the bottom number first, and then we would add on to that. Because of the sigma notation, we would go up to the next number, which is going to be T2. Now, it's always done in ascending order by 1, the way that we're setting it up right here. So if you start at an I value of 1, you go to a 2, you go to a 3, you go to a 4, you go to a 5. When do you stop? You stop when you reach this number up top. So we're going to stop counting when we reach the number 100. So in reaching that 100, we would be done. And what does this mean? Well, it means that we're going to get plus T3, plus T4, plus T5, plus blah, 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 blah. We're going to stop when we get to 100. So what does this mean? This means we're going to take the first 100 terms of this sequence that we have up here, and we're going to add them together. So this kind of means the same thing. Sigma notation, or just that quick, like, just sum the first 100 terms, and that's all that means. All right, so let's write down a way to come up with Sn for any general arithmetic series. So if we know that Tn is equal to T1 plus n minus 1 times d, and we know that T1 is just T1, then if I take the last term and I add it to the first term, the last term, it's Tn, and I add it to the first term, and then I say, let's divide that by 2, because that's going to give me, if I take the first term and the last term and add it, I'm going to get 2 lists. I guess I could divide by 2 at the end, but I'm just going to divide by 2 now. How many of those pairings do I get? Well, I get n of those pairings, because there's going to be n in the list here. So what is Tn? Well, Tn is just T1 plus n minus 1 times d. And then I would have plus another T1 times n all over 2. So I get 2 T1 plus, and then I get that n was in a bad spot. I kept looking back at that. So I'm going to erase that and put it on the outside where it should be. So I needed a bracket there, which I hadn't put, so that's my fault. N minus 1 d, and then times n over 2. So this is one way to write that. Now, the other way to write that is just, in this particular case, if you were doing the Gauss thing specifically, it's just going to be n times n minus 1 over 2. But this is a more general way to write it. This will work no matter what the initial first term is. So we had a first term of 1. For instance, if I fill it in for the Gauss thing, this would be 2 times 1 plus 100 minus 1. I don't know what I'm doing. 100 minus 1 times 1. I'm thinking ahead, but I'm freaking myself out while doing it. So it's 2 plus 99, which is where the 101 comes from. And then the n is the number of terms. So sorry, that should have been 100. And so 2 plus 99 times 100 over 2 gives us our 101 times 100 divided by 2, which is exactly what we had said before. So this thing right here is a way to come up with the general sum for any arithmetic series. So a series is the sum, or the sum of the sequence is okay to say too. So let's write that down again just to make sure it's clear. So the sum can be listed as 2t1 plus n minus 1 times d over 2 times n. So here we go. That would do the trick if you're looking to sum up any general arithmetic series. So if we wanted to, for instance, answer this question, I think I'm going to end here. It says male fireflies flash in various patterns to signal location or to ward off predators. Different species of fireflies have different flash characteristics, such as the intensity of the flash, the rate of the flash, and the shape of the flash. Suppose that under certain circumstances, a particular firefly flashes twice in the first minute, 4 times in the second minute, and 6 times in the third minute. If this pattern continues, what is the number of flashes in the 30th minute? What is the total number of flashes in 30 minutes? So first thing it's asking us for here is come up with T30. And then it's going to ask us to come up with S30. So the first thing I'm going to do to come up with T30 is to say that T30 is equal to T1 plus n minus 1, which would be 29, times the common difference. Now, if I look here, it says flashes twice and then 4 times, then 6 times. That's a common difference of 2. So it goes 2, 4, 6. I also know the T1, I don't have to go looking for either. It's just, I know the T1 is 2. So what that means is that T30 is equal to T1 of 2 plus 29 times 2. So that's actually just 30 times 2, which is 60. So it's going to flash 60 times in the 30th minute. The sum is going to be equal to 2 times T1 plus n minus 1 times d over 2 times n. So I'm just going to double check that. So it looks good. So now we have all the pieces we need to be able to develop the answer to this sum. So it's 2 times 2 plus 30 minus 1 is 29. Common difference of 2 over 2 times the number of pieces there, which is 30. So we get, what, 4 plus 58. So that's 62 divided by 2 is 31, and times 30 is equal to 930. So we flash 930 total times in the 30 minutes. All right, so that's going to be all that I cover for now. I'm going to give you some practice to work with out of the text. But oh, actually, do you know what? I'm going to stop teaching. But if you want, you can try this one out. And I'll just work through it real quick, and then you can compare. You can pause it and try it and see how it goes, and go from there. So do the sum of 2, and so that's 13 according to what the question says. If we put in our general formula and plug in an n value of 2, then it gives us equation 1 that we have right here. If we do the same thing for the sum of the first 4 terms, it's equal to 46 according to the question. Put it into our general equation, and then it will give us our second equation that we have right here. Subtract equation 1 from equation 2. So 13 away from 23 is 10. 2t1 away from 2t1 is 0. 3d d away from 3d is 2d, and so you get 10 is equal to 2d, or d of 5. And we can just kind of pick away at what it is that we need. So I said that since I know that my first two terms are just t1 and t1 plus d, then those added together give me 13. I now know that the d is 5. Subtract that 5 over and get that 2t1 is equal to 8. And then t1 then is equal to 4. So then I have 4, 9, 14, 19, 24, and 29. All right. Take care, folks.